I'm Chintan Parikh. This is Kalpesh Dankara, Payam Bahadurani. We all have engineering background related to process and mechanical engineering, and we do get involved in a lot of these troubleshooting that we'll be discussing later in this presentation. So, as you all know, membrane systems are biological systems, and instead of a clarifier, they have membranes for solid-liquid separation. Uh, it's a biological process and membranes, and there's an interdependency in between them, which is usually referred as biohydraulics, that some of you must have heard it. So we use online analytics as well as membrane performance tracking with a web-based tool, and we use that to optimize the plant performance in terms of meeting your BNR, ENR quality, as well as maintaining your membrane performance. So uh, the focus of this presentation that you will see different case studies where how monitoring a particular specific process parameter improves your membrane performance, or how controlling the process through online data monitoring can help you meet really low nitrogen numbers. In 1999, we started with a process called Symbio, which is simultaneous nitrification, denitrification happening in one basin. Basically, we are controlling the parameters within the one basin, controlling the aeration SRT in a way that you can nitrify as well as denitrify. 2001, we started off with membranes, as Dennis mentioned. That's when we got into the membrane market. 2004 is when we had our first membrane plus Symbio kind of workshop, MBR, UNR, MBR together. And right then, Trevor was here. 2002 is when we had the SND and Symbio with an MBR system. So that was our first MBR plant with simultaneous 99. 2007, we took the next step and kind of, as I mentioned earlier, the whole focus is always process plus membranes. They're together. So in 2007, we took the next step, innovated, and said, okay, how can we make the process even simpler? So we applied for a patent, which is for high solids application, which is instead of running at an MBR at 10,000 milligrams per liter, you would run at 20,000 milligrams per liter. Now, when you do that, you can't really use fine bubble aeration because you're limited by the uptake rate. So we had a high rate with concentrated oxygen as well as single stage SNDN. So that was kind of the next level of innovation. In 2012, again, we switched from flat plates to flat sheet. At the same time, we also had a couple of our first single stage MBR systems doing significant nitrogen removal. 2017, it's more like late 2016 when we had a single stage process doing ENR up to almost more than 94% removal. So that's just a brief background about how we transitioned over the years, how we innovated from a membrane perspective, from a plate technology to a sheet technology, from a process perspective, from a 3-stage, 4-stage, 5-stage to more to a single stage. And from an oxygen perspective, using concentrated oxygen. The whole idea behind this was to make the life simpler for the operators. If something goes wrong in a 5-stage process, you have 5 different subsystems to look at and monitor, control, whereas with S, they're trying to manage and do it in one tank. So from a process standpoint, yeah, it's critical because you have to have the right controls, ability to understand that, ability to change that, manage that. But from a maintenance perspective, it's much, much simpler. Again, as I mentioned earlier, we applied for a patent in 2007. It's a single-stage patent. And since then, we have been always focusing on data. We have been working with several universities. They are doing some testing for us. They have been doing testing. They're collecting data using a SPECE cone. Again, that's used for concentrated oxygen, ability to use concentrated oxygen and adding it in mixed liquor in a high-rate system, 20,000 milligrams per liter. And all that data so far indicates, or have been indicating, that you can achieve really low nitrogen in a single-stage system as well. So starting our journey from 5-stage to 1-stage has been a long journey, but we are there. We have data for the last 10 years that shows that it's possible. There are a few case studies next, and this one is a single-stage design. That's the one zone. The target TN was a TN of 10 milligrams per liter. The influent was about 60 milligrams per liter. BOD, about 400 is the design. TSS 300. So it was a little bit more than your typical municipal waste. And from a removal standpoint, you're removing from 60 down to 10. So that's more like 82, 83% nitrogen removal. So you can call it as a BNR design. Now doing it in a single stage, again, we are controlling the aeration, but at the same time, this is a high rate system. So it's 20,000 milligrams per liter. So it has a concentrated oxygen and a ductor to be able to add that oxygen into the system. The way it's controlled is you are looking at a DO measurement and trying to control a DO in a certain bandwidth so you are able to achieve nitrification. And then you go to a lower DO to get to denitrification. And you may add carbon as needed because the BOD to carbon ratio also needs to be adjusted when you're doing single stage designs. Now from the trend, you can see the top green is the actual loads that's coming into the system. So the design was 60, and for more or less it was an average of 60, you can say, but there are some days where it was 70 or above. From an effluent standpoint, it has always been less than 10. Now, if you were to ask this to somebody 10 years back, anybody would like, how is this possible? You know, how can you do nitrification, denitrification both in one basin? But we can, and it has been out there for the longest time in oxidation dishes, where you have the rotors, and as the water moves away from the rotors, you get more denitrification. So it was there, but there wasn't an ability to control. Now, what we have been doing over the last several years is have online analytical tools. And when I say that, I'm referring to more like your DO meter, your MLSS probe, or your effluent ammonia monitoring probe or nitrate probe. When you have that, you exactly know what your plant is doing. Then you can control the oxygen, you can control the carbon dosing, you can do a lot of things. So having the ability to have those tools is really critical. At the same time, from a membrane perspective, we try to monitor performances for the membrane specific, like flux, permeability, your air scour rates. So when you combine them both, you have a pretty good idea from a biohydraulic standpoint and how changing one parameter can affect your other performance as well. So keeping that in mind. But one other thing to kind of take away from this is that this plant was having a flow rate of roughly about 50% of the design. So from a mass standpoint, it was underloaded for the system. So it was meeting the limit in a single stage design, but it was a bit underloaded. Second example, similarly, single stage design, the influent characteristics were more or less the same. Influent nitrogen coming in at 60, effluent target was 10. Same thing, high rate system, so it had a operating MLSS of roughly 15 to 20,000 milligrams per liter, and it needed a concentrated oxygen system with an inductor to push that oxygen in. And this system is meeting TN as well. 80 to 83% removal in the single stage, and this system was also underloaded. Still more than 50%, but less than 100% from design. This case, the third case, again, it's a single stage. So all of these, keep in mind, just have the membranes only. There's one basin with membranes only, no anoxic, nothing. And these systems have been doing pretty well. So this particular case had a flow of about 20,000 gallons per day. And right from startup, the flows went up, or actually started off, much higher than design. There were times when the flows were 30, 35,000 gallons per day. So from a process standpoint, you can tell that they are already much above the design loading. It's about 130% of the design, right from the beginning. So even though it says 3.6, I'll come back to that, but the design for this was for a TN4. And when we first started the plant, of course, it had its challenges, and we were able to get down to TN4 at several occasions. But since it was such a fluctuating flow, it was hard to control in that small bandwidth, because going back to the earlier cases, I was saying TN removal is very critical for any facility. How much are you trying to remove? For the earlier ones, it was 60 down to 10, which was roughly 82, 83%. For this, the design was more like 75. So you are trying to remove from 75 down to 4. So you're looking at almost 95% nitrogen removal. So having that precise control was very critical for this job. So ultimately, okay, what's up with this case? How can we make it work? So it was designed for a single stage, as I mentioned. It had alum addition for phosphorus removal and carbon for micro C. So the original design was for TN4, but then since the flows, it was re-rated from 20,000 to 25,000, and all this is after it was installed. Since the limit was a pounds per day annual average, once they re-rated the flow, they had to reduce the effluent TN concentration. So from 4, it went down to 3.6. So it got even tougher from a removal perspective. And as you can imagine, if you are getting 130% of the flow, you don't really have enough biomass in the system. You cannot, you can go up to a certain limit, but if you're limited with biomass, you can't really achieve your limits. So that was a big challenge. So ultimately, the option here was to add additional anoxic step. And this was to get a more consistent, reliable effluent quality. As I mentioned earlier, we were able to get it for some days, but then some days it was out of control, just because there was a very narrow bandwidth. So we added a separate anoxic tank. Now we are doing dedicated denitrification. We're still adding carbon through micro C as needed. But adding the extra anoxic tankage helped in getting the dedicated denitrification time, as well as being able to increase the SRT, because now you have more volume, so you can increase the MLSS through SRT increase.
So to meet tight TN limit with only 2-zone system at more than 130% of flow capacity required online analytics, increased lab testing, remote access to the data, process data, online process data, and easy access to data to multiple parties, and real-time continuous performance notification. So we take actions based on the notifications, and we used multiple platform to do this. And here you can see that the top chart is from CRM software, which OVO uses, and the bottom one is a chart from the ZAPS unit, which monitors the online analytical data like BOD, TKN, nitrate, nitrite. So customer was getting their TN within the limit after installing the additional anoxic tank, and suddenly they stopped getting the TN in their permeate. And when we started looking into this correlation with a different platform, we found that there was a relation between EQ tank level and TN in permeate. So if you can see on the top chart, which is showing the red line, the horizontal red line, customer was maintaining certain equalization tank level, and since they wanted more capacity in the EQ, they dropped it to low level. And when they dropped it, immediately their permeate started getting TN fluctuations and not meeting the norms. So here the problem was their inlet quality was changing, the concentration coming to the plant was changing, and when they were maintaining certain volumes in the EQ, it was equalized, loading was equalized, and stable number was coming to the plant, and that's why they were meeting the numbers. So after finding this correlation, we requested customer that you may want to put some buffer in your EQ and at least maintain certain fits in your EQ tank and start dosing a little bit more micro C, so have more buffer in the system, so if small fluctuations is coming to the plant, it can be taken care by that micro C. And when they implemented these changes, they again started getting the TN within the norms. So we used online platform to help customer and plant like this where to meet very tight TN needs multiple platform to stabilize the system. So on this chart, it shows the permeate quality in terms of TN numbers. So you can see at the beginning, we used to struggle with the TN. That's where the flow was coming high and single tank system was. And when we introduced the pre-anoxic tank, customers started getting TN within the limit. The average TN here at 25K gallons per day was 3.6, which is the limit was. And in 2017, this number was like 2.85 ppm in permeate. With the new case, this was like single zone system, a microblock system, package plant, and designed for 22,000 gallons per day for TN less than 10. So, and this plant was commissioned last December. At the very beginning, when we seeded with the good quality sludge, suddenly the TMP was rising quickly and they were doing frequent CIP. So we involved in this and customer was raising the question that your membrane is not doing good. It's a new membrane and still we are doing frequent CIP. So we started looking for data from them, and when they shared the data, we could feel that their sludge quality is not good. And we started asking more data to them, and at the same time, we requested them to add MP50. So they dosed MP50 at the commissioning stage. It was helping them, but it was not sustained. So they were still doing the frequent CIP. And when we got the data from them, and we saw that their inlet is coming with the low in alkalinity. So with the low alkalinity, pH was dropping in the process, and because of partial nitrification, the sludge quality was not up to the mark, and that's what causing frequent CIP and raising TMP quickly. So in this chart, you can see that on left-hand side is the sludge filterability number in terms of blue line, and on right-hand side, it's a effluent alkalinity number. So when customers started adding alkalinity to the plant, and you can see in the permeate, the alkalinity was above 80 ppm or somewhere around 80 to 100 ppm. Their sludge filterability started climbing up. That's where we have seen that, there was an issue with the alkalinity, and it was affecting the sludge filterability. So here I have shown the same chart, left-hand side TMP, right-hand side flux. So when there was no alkalinity addition, sludge quality was not good. Their TMP was raising quickly. But when they started adding alkalinity, their sludge quality maintained. The sludge, the TMP was more sustained and not raising quickly like earlier, and their CIP frequency also reduced. So in this case, we found the relation that observed effect on the plant was frequent CIP. That was because of TMP, and TMP was raising quickly because of sludge quality. And we could able to identify our root cause was low alkalinity coming into the plant. And the solution for that was add alkalinity, maintain pH. So here is the case that when you have an issue with your membrane, people start questioning on membrane. But it's not all the time membrane, it's a biohydraulics, it's a combined system working together with the sludge. So we need to find the root cause to fix the problem. There are short solutions like chemical addition and all, but those are not the proper solution. We have to go to the root cause and find the real solution, and then only it will solve the problem for permanent.
Hello, everybody. As my colleague explained, I'm going to talk about the importance of data availability and online data availability and field observation, and how it's going to help us to improve and optimize the system and troubleshoot the system. And this case is about what if nothing makes sense. So I'm talking case 5 about a simple MBR system, three-zone system. It's a new community coming to the underground EQ basin, pump to the bar screen, forward to the anoxic, pre-aeration basin, and MBR basin. That's a schematic. It's a very simple plant. The challenge here we're facing, we had almost double loading than what the plant designed for. So the plant originally designed for TKN of 45 milligram per liter, but the actual TKN was, influent TKN was 80. We had high spikes such as 200 milligram per liter, 133 milligram per liter, 180. So we had lots of high spike of TKN. So double loading the temperature was designed for 15 degree Celsius minimum temperature, but the plant was operating at the 8 degrees Celsius for a long period of time. So all those impacted the process, and with online data and historic data, field observation, we were able to optimize the system and meet the TN permit and exceed the TN permit. So as you can see, once we commissioned the plant, we had all the right tools for nitrification and denitrification, but we had lack of nitrification, and we had aeration, we had everything. And then suddenly we have like a smooth drop in the curve. The red dot shows that we start nitrifying. So we're suspecting, I mean, nothing makes sense before, so we had inhibited nitrifiers. And then ammonia in effluent, we get almost zero, but still we had lack of denitrification. So through the data analysis and field observation, we were able to troubleshoot and optimize the system. And in this case, the lack of denitrification was due to high DO in anoxic basin, improper mixing, and low BOD due to high influent TKN. In next few slides, I'm talking about the also importance of the field observation and details that only a trained operator or technician can note those details, and a normal person usually don't see it or they don't care. One example here is mixing. Mixing is very important in MBR system or in biological system, and we had a huge underground EQ basin without mixing, so it was covered. So we had septic condition, and every time we pumped the influent to the bar screen, we overwhelmed the system and upset the biology. Another challenge was proper mixing in other basins, such as anoxic basin or short-circuiting, another sort of mixing issue. If you have short-circuiting, we have dead spot in basin, which is causing septic condition, and short-circuiting in other section of the basin, which is basically we have shorter retention time as we designed for. So we try to avoid all those. One of the important key factor in MBR system also, as my colleague explained earlier, is screening. Proper screening is very important. So in this plan, as we see, we had screen bypassing, and I'm gonna go through the picture. Screen bypassing could cause clogging or equipment failure or compromising the equipment performance. So those are all critical factors you need to consider. Here, as you can see on the left side, there is a cable and a big ragging hanging off of the cable, which is due to bypassing the screen and causing issue. On the left side is another, I like the left side picture. It shows the pre-aeration basin and diffuser at the bottom. If you look at, there is a layer of the solid at the top of the diffuser, and this caused because of turning off the pre-aeration blower. So the plant thought the oxygen, high oxygen from pre-aeration basin carry over to anoxic basin. So they turned off the blower for a month or so to try to see if it could improve the denitrification. After they turned on the blower in pre-aeration basin, they couldn't get to the original set point. So we drained and inspected the basin, and we noticed that the diffuser was fault, so we were able to wash it and clean it. It was simple, but we had to drain the basin to be able to clean the diffusers. So basically, not mixing in the pre-aeration basin causing septic condition and also equipment failure. The right picture shows the sample of the EQ basin, which it shows we had septic condition by lack of mixing. And this is another picture of the freezing. We had freezing. It could be freezing of a piping or chemical feeding. This is for sodium hydroxide. The interesting of this slide is sodium hydroxide 50% solution. freeze at like 52 degrees Fahrenheit, if I'm correct. But the 25% solution freeze at 0 degree Fahrenheit. So that was really interesting. So to summarize the case number 5, the problem we had was we had high total nitrogen in the effluent, and the root cause to that was having significantly higher loading, having ammonia toxicity, lower temperature. We had short-circuiting and clogging. Those were the major issue we had. And by having the available data, historic data, we could look at it, analyze it. We were able to troubleshoot and optimize the system. Basically, we needed the data. In this case, we needed the influent effluent quality. We need to know the temperature of the mixed liquor, pH, alkalinity coming into the plant to see how much we have available, and make sure we have equipment running properly, mixing, we have proper mixing, everything. So field observation again. And the solution to that, we collect all the data from the field and from the online available historic data, and we model the system based on the new values. And we were able to establish a roadmap to optimize the system with the new parameters and make field adjustment. One of the, for example, simple field adjustment we made was the pre-aeration blower, or MBR blower. So we make it that we provide efficient air for the aeration basin for nitrifiers, but not over-aerated to impact the anoxic basin. So the result was short and sweet. We were able to meet and exceed the TN limit of the 7 milligram per liter with the double loading. Basically, as I mentioned earlier, the plant designed for 45, but the actual loading was 80 and above milligram per liter.
There will be problems. We all know there will be process problems. There could be mechanical problems. There could be membrane-related problems. And how we figure out based on using data is ultimately, it boils down to. When we have a process issue, it's good to have a model run. Run your model until you're able to actually mimic the actual effluent quality and then try to improve it. We used to do that before on systems. We still do it on now. But that helps us determine what's the root cause, what's the particular parameter that's missing, how do we change a particular kinetic in the model to get the results that we want. So modeling to match your effluent quality and to be able to meet the permit is one thing we would suggest. We all know that when you have if your loading coming into your system is more than design, then you are going to run into issues. And especially when you have really low nitrogen removal, upwards of 90% or so, that control becomes even more critical. So having the ability to have online real-time monitoring tools really helps to be able to have a quick effect, a reaction to your process. Biohydraulics, process, and membranes are related, and they do play a critical role. As we discussed in some of the earlier cases, even though your process seems to be running fine and membranes are not doing okay, a simple adjustment as alkalinity can really help your membrane performance. So keep that in mind as well, that process plays a critical role in your membrane performance. And in the end, sometimes when data doesn't help, there is physical observations. There is no substitute for manpower and our input and what we see and how we can interpret that data and actually resolve those issues. So at the end of the day, the whole point of this is data monitoring, online monitoring, as well as membrane performance tracking is really, really critical to achieve really low TN systems, really low ENR type results. So that's all.
Okay, thank you very much, guys. Any questions from the floor? I got one. It's kind of cruel, but if you're going to design a plant that's SNDN, and then you have to put in a pre-anoxic tank. Wouldn't it have been just as good to design it classical with denitrification and aerobic in the first place? Just asking.
Yeah, it certainly is an option to do that from the beginning. Why not? You know, we could design a 5-stage system for that matter. I mean, instead of going to 2-stage, if it was a 95% removal, we could design a 4-stage, 5-stage system. But ultimately, it boils down to the cost of the project, and as well as O&M, maintenance, and all that. So, yes, it could be designed that way, but there's a cost impact, there's a CapEx, OpEx impact, and ultimately what's driving that project makes, whatever the demands are for the project is how we approach and provide a solution.
It's interesting, isn't it? Because SNDN does demand a lot of control, and you were saying right at the front end, now we have the control, but of course you still can't sort of legislate against massive changes in load, because then that just kills everything anyway, I guess, because you've only got that much tank size and that much microorganisms to sort of mitigate against those things.
Right.
So.
Yeah, and if it was below underloaded or even at the design 100%, we could have managed it, because we did see several occasions where we were meeting TN4 at that design flow, but it was over-designed. I mean, it was not over, it was overloaded. It was 130% of, so that was the bigger challenge here. It wasn't actually the low TN, which was a critical parameter, but it was over-designed. That was the part that hurt us.
Yeah, we're back to the Gumpian box of chocolates where you never know what you're going to get, Forrest. Yeah, you've all seen it. Any other questions? Yes, sir. So did you incorporate ORP into the control strategy?
Right.
So just repeating so that everyone can hear
So
that.
for this facility, we did not have ORP, but we had effluent monitoring, where we had analytical real-time monitoring. We were monitoring effluent ammonia, effluent nitrates. Of course, there was DO and TSS monitoring. And we were monitoring that. I think you saw it in a couple of slides, but we were monitoring the effluent ammonia and nitrates to be able to adjust the carbon dosing, alkalinity dosing, as well as oxygen control to be able to get TN, low TN. Right. ORP is a good as well. We have used it on some jobs. And in this facility, we didn't have that. We had other tools.